Alrighty, howdy folks. Let's move on to section 3 in chapter 13, and this is about arc length and curvature. Just to give a quick recap, we are looking at space curves or vector functions. Vector functions meaning r of t. So the r is actually a vector. Earlier, we saw what they look like. For instance, you could draw a space curve knowing that r of t, a vector function r of t, is of some form of vector f of t, g of t, if there is a third component h of t. Those are the x, y, z components of this vector r. And we can create a function out of it, and we have drawn space curves and all that. Now we are going to look at a few additional, what should I say, parameters and additional concepts on those vector curves, on those space curves and vector functions. Okay. The very first one that comes to mind is the arc length, the concept of arc length. Can you guess as to what that is? Suppose you have some kind of a curve. Couldn't you just run a piece of string that falls right on top of that curve? And then from some point A to B, you put a string and then pull it out and measure that length of that arc. In a sense, your string may have followed the contour of the space curve, but now you stretch it out and measure the length. That's going to indicate the arc length. As a simple example, just look at a circle. What's the arc length of a circle? Well, isn't that the same thing as the circumference of the circle? If you were to run a string all along the circle and come back to the original point, and now you got a string that has taken a circular shape and now stretch it back to a straight line, and what would its length be? Equal to the circumference. So when we talk about arc length, the curve need not be a nice circle, could be anything. That's the whole idea. Okay, so how do you find the arc length for a space curve? So here the definition says, if we have a space curve expressed as r of t is f of t, g of t, h of t, those are the x, y, z components of that position vector r, which we could write like this as well, then the length of the arc. Now here is the interesting thing. When we talk about the length of the arc, then we have to say from t equals what to t equals what. So the interval is stated as t equals a to t equals b. And how do you find that? By simply integrating the arc length is L, and integral a to b of square root of f of t, the f prime of t, the quantity square, plus g prime of t, the quantity square, plus h prime of t, the quantity square. But what is that f prime of t? Well, we said f is the x component. So if you were to take the dx dt, that's precisely what f prime of t is. Okay, and you square it, similarly dy dt, and so on. But then when you recognize that this is nothing but the magnitude of r prime, right? Magnitude of a vector is what? Square root of the x component square plus y component square plus z component square. That's exactly what we have done. And so this is nothing but the magnitude of the r prime vector. Okay, integral of the magnitude of the r prime vector. Okay, that's how you find the arc length from t equals a to t equals b. Now we have what's called an arc length function. Didn't we already discuss arc length here? Then what's up with this arc length function? Look at this. If a space curve is expressed as r of t, and a is less than or equal to t less than or equal to b, okay, then the arc length function is given by this, apparently. Take a look at this. Isn't that the same as the previous one, man? No, it's not quite the same. This is actually a function. The previous one gave you a number. It gave you the exact arc length from t equals a to t equals b. But what this does is gives you the arc length as a function of t, meaning, please pay attention to this. This gives the arc length as a function of t. What that means is, starting at t equals a, if we go to any arbitrary t could be 1, 2, 3, 4, 1.5, whatever number you pick, you should be able to tell what the arc length is to that particular t. When you do that, in a generalized fashion like that, you have an arc length function. Cool? That's the difference. Okay, so notice the change in the limits. Here we had integral a to b, but here, however, we have integral a to t. What's the difference? A and b are constants, whereas a is still a constant here, but t is a variable. Cool. Integral a to t, dx du the quantity square. What did we have here? Dx dt the quantity square. Okay, dy du the quantity square, and we are integrating with respect to u. Earlier we integrated with respect to t. Why did they do that? Couldn't we say dx dt the quantity square plus d, and so instead of u, couldn't we have a t here? The answer is no. What? Why not? It's because the t is a variable here, which happens to be our limit of integration. So you cannot integrate from a to t and have a t as a variable here inside the integral. So that's why typically what mathematicians do is they use a different variable. Is dx dt kind of the same as dx du? Of course it is. But it's just that you cannot call it, you cannot have the limit of integration to be t, and you could be integrating with respect to t. You see that? That's the only small difference. Okay, and the rest of it is the same. Integral a to b, well, integral a to t of r prime of u du. Should we call it u? No, you are free to call it alpha, w, whatever you want. So u is a sort of a dummy variable. Your original function, maybe that's another thing that I should point out. The original thing we have is as a function of t. Okay, man, if I have r of t as f of t, g of t, h of t, then how can I do dx du? Well, if you know f of t, couldn't you figure out what f of u is? For example, f of t, let's say that is equal to sine t. Guess what f of u is? Sine u. As simple as that. Cool? All right. So we can have an arc length function as well. And, excuse me, I'm going to cough. And here, what this implies is ds dt. What's it? This is the derivative of the arc length function s with respect to t is nothing but the magnitude of the r prime of t vector. Cool? How do you get that? Look at this one. Is it true that if s of t is equal to integral a to t of absolute value of r prime of u, magnitude of r prime of u, du, then ds dt will be magnitude of r prime of t? Yes. Do you remember that fundamental theorem of calculus? It says the derivative of the integral of a function is the function itself. The easiest way to put it is the derivative of the integral of a function is the function itself. That's a colloquial way of saying it. There is in fact a more formal way of stating the fundamental theorem of calculus. What you're supposed to do is make the composite function r prime of whatever this upper limit of integration is. If upper limit is, say, h of t, some function h of t, then you have r prime of h of u here. In the r prime in the final result, you'll have r prime of h of t times h prime of t. Are you with me? Let me repeat that. Had the upper limit of integration be h of t, then this integral, according to the fundamental theorem of calculus, would be this derivative of this would be r prime of h of t times h prime of t minus r prime of the lower limit a times the derivative of a itself. But a is a constant, so its derivative is 0. Okay, and here our h of t that I talked about is just a simple t, and so we have r prime of, instead of r prime of h of t, we have r prime of just t times the derivative of h of t itself. That means h prime of t. Well, if h of t is t, would you agree that its derivative is just 1? So shouldn't we just be multiplying by 1? Yeah, so this is just r prime of t. Cool? Magnitude of r prime of t. Okay. What else? By fundamental theorem of calculus. And there's another concept that we need to learn, which is called, when would you say that a parametric curve is smooth? A parameterization r of t is called smooth on an interval I if r prime is continuous and r prime of t is not equal to 0 on I. Okay, the continuity part has to make sense for something to be smooth. If there is a discontinuity, let's say there's a jump discontinuity, obviously the curve is not smooth because the curve was following, say, a nice path, and all of a sudden there's a jump, there's a discontinuity, then the smoothness is affected. Just the intuitive way of looking at it. And while that is one aspect of it, here is the second aspect of it. R prime of t cannot equal 0. I must tell you, that thing just threw me for a loop. I was like, what? Why couldn't r prime of t equal 0? Now, the reason that threw me for a loop is because, let's go back to just y equals f of x kind of a function. Could we say f is a smooth function? When would we say that? Oh, when f prime of x is continuous, could be 0. If there is no problem with f prime, then we would say, yep, that is a smooth curve. If the first derivative is continuous, then we say the function is smooth. So, according to that, something like a parabola, y equals x square, or f of x equals x square. Clearly, at x equal to 0, we have the derivative f prime of x to be 0. Does that make a curve like y equals x square not smooth at x equal to 0? Answer is no, it is still smooth. Then what's up with r prime of t cannot be equal to 0? Right? Uh, that, man, I had to think a lot about it and discuss with my colleague, Dr. Andrew Hetzel, who was very, very helpful in clarifying some things for me. Okay, I'll show you in the next slide. Cool. A smooth curve has no sharp corners or cusps. And also, when the tangent turns, it does so continuously. So that's when we would say a curve is smooth. A smooth curve has no sharp corners or cusps. Cusp is kind of like a kink. All right, and now consider a parametric curve r of t equals, let's just go to R2, I mean a two-dimensional one. I wanted to draw this and show you what we mean. So if we have this, the question is this smooth? Okay, smoothness is based on what? R prime of t should not be equal to 0. R prime must be continuous, right? Cool. So let's figure out what R prime is. How do we do that? I just simply take the derivative of each of those component functions. T cubed, the derivative is 3t squared. The derivative of t squared is 2t. That's what I have. Simple? Cool. R prime of t, we got that. So is this continuous? Look at the component functions. 3t squared, 2t. Are they nice and continuous? Yep, they are. So R prime of t is definitely continuous. Now the question is, could R prime of t ever be equal to 0? Right? Well, sure. When t equals 0, 3t squared will go to 0 and so will 2t. So R prime of 0 is in fact the 0 vector. Oh, by the way, when they said R prime of 0 is equal to 0, that's the 0 vector. So R prime of 0 is in fact equal to 0, the 0 vector. So what happens? I actually went ahead and drew this parametric curve. And it, sure enough, at t equal to 0, there is a cusp. See that sharp corner? And definitely, we can say that, nope, this parametric curve is not smooth at t equal to 0, which happens to coincide with x equal to 0, y equals 0. But t value is the one which is 0. Okay, so they were right. If R prime is 0 at some place, there is an issue. There will be the curve, the parametric curve won't be smooth there. So this example at least is a good example to show that. But then I asked myself, wait a minute, I'm not so sure that actually works here. And what did I say here? Yeah, note that 0, 0, we have a cusp and the parametric curve is not smooth there. Okay, yeah, fine. Now, I wanted to think about this parametric curve, t cube comma t cube. By the way, if we convert this to Cartesian, this is our x, right? X is t cube and y is t cube. What? X is t cube and y is also t cube. So are we saying y equals x? Yeah, we are. Okay, so what kind of a parametric curve would this be? It would be that curve, that line y equals x. Really? Yeah, really. So we could in fact convert, at least in some cases it's fairly straightforward, convert a parametric curve to an equivalent y equals f of x or x equals f of y. Okay, or some kind of a implicit function of x and y, sometimes. All right, so let's see with this one. R prime of t, of course, is 3t squared comma 3t squared. Will this ever be 0? Yep, at 0, at t equal to 0, this is 0. Just like the previous one. So the previous one, when the R prime of 0 was 0, we had a cusp. Will this have a cusp at t equal to 0, which is x equal to 0, y equal to 0? Nope. So I wanted to ask I asked my colleague, would you say that this curve is not smooth? If I show you a line, is a line smooth? The answer is yes, because its derivative is continuous. So as a parametric curve, this is not smooth? And he said, yep, you have to say that this curve, this parametric curve is not smooth at t equal to 0. I said, why? Oh, because like the condition states, r prime of 0 is 0, but it doesn't have any cusp. It doesn't matter. Why doesn't it matter? He said, well, it doesn't matter because of something that we are going to look at in just a second. There's something called a tangent vector, a unit tangent vector. You wouldn't be able to tell which way that unit tangent vector is. Even though there is no sharp corner, it appears to be visibly smooth. Technically, this parametric curve is not smooth. And in fact, if you want to try r of t equals t cubed comma t to the 6, where you have x is t cubed, y is t to the 6, right, which is the same as y equals x squared, you get a parabola. At t equal to 0, how does that look? Well, as a regular parabola, y equals x squared, there is no issue with the smoothness. But when expressed as a parametric curve, yep, there is a problem there. Okay, so it is related to what? A unit tangent vector not being able to be defined or not existing at that point. That's what the problem is for smoothness. And we'll talk about precisely that. Note that 0, 0, we do not have a cusp, yet the parametric curve is not smooth there at that point. I'm going to talk about the unit tangent vector right after this, but let's do one more thing. Parametrizing using arc length S. What is this? Parametrizing using arc length S. What were we parametrizing the curve before? Oh, with t. Is t and s related? Yeah, we talked about the arc length function s as a function of t, the parameter, right? S equals some s of t, some function of t. Okay, if s is a function of t, could we write that as t being some function of s? If y equals x squared, y is a function of x, y equals x squared, can we say what x is? Yeah, x equals square root of y. Can we always do that? No, there may be some situations where you cannot invert like that. You cannot find the inverse function quite easily like that. But that concept should not be that difficult to grasp. So even though the original function is in certain situation, it is useful to parameterize r of t in terms of its arc length s. So here we'll say t is equal to some t of some s, and so r of t becomes this composite function r of t of s. Okay, so we could do that, and that comes in handy in just a second. All right. Definition. Unit tangent vector. We are here at the unit tangent vector. Unit tangent vector t of t, the very fact that we are saying it's a unit vector, that means its magnitude has to be 1. Okay, what exactly is it? We know we know the R of t, function R of t, right? Vector function. Can we take its derivative? Yep, that's what our R prime of t on the top is. And then we divide that by the magnitude of that R prime of t, and that's how we get the unit tangent vector. Unit tangent vector is a pretty important one. So basically, especially as engineers, we should be concerned about this unit tangent vector, because you can imagine if we have a space curve R of t, think of a roller coaster. It's a curve, right, in space. Yeah, think of it as just a line, even though it's got width and all that stuff, width and height and all that. Think of just a single rail of a roller coaster, maybe. Now, a particle, a certain particle, what should I say? Let's say do roller coaster, the cars that you sit in, do they have wheels? Okay, one of the wheels is traversing along the track, right? So think of that as a particle that is traveling along that curved track. Now, it's moving with a certain speed. What is its direction? Or how could you talk about the velocity of that as a vector function? Well, whatever speed you are going times the unit tangent vector tells you the velocity vector of that point traveling along that space curve. Cool? All right, so we need unit tangent vector as a practical thing. Of course, mathematicians need it for many, many other reasons, but that's one practical thing that I can tell you about. All right, and how do you compute it? Fairly straightforward. Take the derivative of R, and you get R prime of t, and divide that by the magnitude. Ta-da, you're done. And then there's something else called curvature. A curvature is given by dt ds. Okay, dt ds. The derivative of the unit tangent vector with respect to what? With respect to that arc length. Okay, and it can also be written as the magnitude of t prime of t over magnitude of r prime of t. And I'm not going to derive this thing, but we can show that in fact this is r prime of t crossed with r double prime of t, magnitude of that, divided by r prime of t, the quantity cube. Okay, derivation is just a little bit of a pain, so I'll leave that. Where t is the unit tangent vector, s is the arc length that acts like a parameter t. Okay, and it's in the curvature definition that we needed to express arc length and think of s as a parameter. That's why we defined parameterizing using arc length s. Okay, cool. And then there are a couple more things, the normal and binormal vectors. Graphically, let me show you what those things look like. If this is a space curve, can you see that the tangential curve, the unit tangent vector, is this one? It's tangential to the path. Well, strictly speaking, we are as a particle traveling along the curve. If we think in those terms, the particle, imagine, is traveling along from the bottom corner here and moving that way. If it is moving in that direction, its velocity at that particular point would be pointing that way and tangential to the curve itself at that point. And the unit tangent vector would be pointing that way. Now, perpendicular to that tangent vector, there is a vector called n of t, and that's the normal vector. What's the relationship between t and n? They're perpendicular to each other. Well, aren't there infinite number of vectors that are perpendicular to t? Yeah, they are. But this n of t, the normal vector, has a certain special condition. Maybe I'll show that. Well, from the figure on the right, we understand that the tangent vector is tangential to the space curve. Yeah, that's the point. What about the normal curve? Normal vector? The normal vector n of t is perpendicular to the tangent vector, like I said. And there's one more thing that it does. And it indicates the direction in which the curve is turning. Okay. If this is veering a little bit to the right, the normal vector would be pointing to the right. Not only is perpendicular to the tangent vector, but pointing the direction in which the curve is turning. Cool. And the binormal vector is a fairly straightforward one. This binormal vector, bi, the very fact that we are using bi means two. It's normal to two things. Which one? Normal in the sense perpendicular to two vectors. Which vectors? One vector is the tangential vector, unit tangent vector, and the other one is the normal vector. So it is perpendicular to both of them, this binormal vector. And each of these vectors will become useful. We will do quite a few things at a later stage. So try to be as familiar with these as possible, please. Cool. All right. Next, let's go to, I just gave a summary of the whole thing. That's it. So I'm not going to spend any time because we already discussed these in detail. In a set of notes, I think it would be beneficial to have this as a summary. All right. Next, I'm going to solve a few problems. I apologize if I'm insulting your intelligence. Find the length of the curve. Find the length of the curve, meaning arc length. We are given R and we are given A and B. A less than or equal to T less than or equal to B. So this better turn out to be a number when we find the length of the curve, because we are given specific constant values for A and B. That means T is specifically from 0 to 1. What's the arc length there? Okay. Any idea what the formula was? Right? What is X here? X is that X of T. I mean the X component of this one. dx dt. What's the derivative of T? Just 1. That's what we have. What's the derivative of T square over square root of 2? Derivative of T square is 2T. 2T divided by square root of 2 is square root of 2. So square root of 2 times T. And that we need to square. And the derivative of T cube over 3 is 3T square over 3, which is T square. And we need to square the T square. Right? That's just simple plug and chug. Okay. Does this remind you of something? Does it look like something? 1 square plus square root of 2 this becomes 2t square. 1 square plus 2t square plus t square square, or t to the 4. Hey, isn't that a perfect square? Isn't that in the form of a square plus 2ab plus b square? A is 1, b is t square. So let's check. Is the middle term like 2 times a, 1, b, t square? Is the middle term 2 times 1 times t square? Yep, the middle term is 2t square. So this is in the form of a plus b, the quantity square. So guess what? This is just nothing but 1 plus t square, the quantity square, of course, under the square root. Oh, that's easy to the square root of this should be just t square plus 1. Strictly speaking, plus or absolute value of, it is a plus or minus, no, absolute value of t square plus 1, but since t square plus 1 is always going to be positive, absolute value of t square plus 1 is just t square plus 1. So we'll confidently go ahead and say, yep, this integral 0 to 1 of t square plus 1 dt, and the rest is calculus 1 stuff. T cube over 3 is the integral of t square. The integral of 1 is t, and we evaluate it from 0 to 1, and ta-da, we get 4/3. Did we get a number for the length of the curve? Yes, we did. But isn't that fascinating? If somebody were to draw apparently this curve, space curve, and run a string all along the curve and see and stretch it out, see how long it would be, it's guaranteed to be 4/3 units. If we are talking about inches, 4/3 inches, 1/3 inch. Fascinating. Cool. Next, find the length of the curve. Okay. What's the idea? Again, 0 to pi/4, constant numbers. So this is not a function of that. So we simply say dx dt, plug, okay, dx dt. The derivative of cosine t is negative sine t. Derivative of sine t is cosine t. Derivative of natural log of cosine t is negative tangent t? How come, man? Well, natural log of cosine t, isn't the derivative 1 over cosine t times the derivative of cosine t itself, which is negative sine t? So 1 over cosine t times negative sine t makes it negative tangent t. And we square it. And obviously, this whole thing just is equal to secant square t, right? Is it obviously? Come on, man. Yeah. When we square negative sine t, would we get sine square t? Is this plus cosine square t? Sine square t plus cosine square t is 1. Cool. Negative tangent t, the quantity square, is plus tangent square t, right? Do we have 1 plus tangent square t under the square root? Yep. Okay. 1 plus tangent square t. You remember the trig identity? That's secant square t. So square root of secant square t. But that's nothing but, uh-oh. Why do I goof like that, man? I'm such an idiot. I thought I checked. Crud. Let me pause, fix this. Alrighty. I hope I fixed it. It's amazing, man. That's why proofreading, when you write your dissertation or thesis, when you get to master's or PhD, what you write, it is impossible to proofread yourself, because you see things you see things that, how should I put it? You do not see things that you are supposed to see, because your mind works in a weird way. Anyway, so we got to this stage. 1 plus tangent square t is nothing but secant square t. Square root of secant square t is just secant t. Like an idiot, I had secant square t earlier, and that made the integral much simpler. Integral of secant square t is tangent t. But now that I have to say that this is integral of secant t, integral of secant t, you remember that one? Natural log of absolute value of secant t plus tangent t. Okay, and so we have that, which we need to evaluate from 0 to pi/4. So plug the upper limit pi/4 and subtract from that, plugging what you get when you plug the lower limit, this secant of pi fourths is the reciprocal of cosine of pi fourths. Cosine of pi fourths is square root of 2 over 2. So secant of pi fourths would be reciprocal of that, 2 over square root of 2, which is just square root of 2, right? And tangent of pi fourths is just 1. So this is just the inside stuff is square root of 2 plus 1. Natural log of that on the outside. Secant 0 is 1 because cosine 0 is 1. Secant 0 would be 1 over 1, which is 1. Tangent 0, however, is 0. So we have natural log of 1. Natural log of 1 is just 0. So this simply is natural log of the quantity square root of 2 plus 1. Cool? All right. So that's how we find the arc length of this parametric curve from 0 to pi fourths. Straightforward. I'll probably ask a simple question like this for the homework. All right. Find the vectors t, n, and b if r of t is this stuff at 1, 0, 0 at a specific point. In general, that would become a pretty hairy thing, but as at a specific point, fairly straightforward. Okay, so in order to find t, we need to find r prime of t and divide that by the magnitude of r prime of t, right? So we have, let's see, is r prime of t negative sine t cosine, like I said? Yep, again, cosine t, the derivative is negative sine t. Wait, is this the same as the one I had before? Dang. It's the same cosine t, sine t, natural log of cosine t. Oh, okay. I'm pretty clever. All right. R prime of t. So I already talked about the derivative of it. And now, yeah, I did that because, things become at least straightforward. This is, again, 1 plus tangent square t is secant t. Guess what? I didn't goof up here. I did call it secant t. Anyway. So, sine t over secant t is the same as sine t times cosine t. Right? Cosine t over secant t is cosine t times cosine t. Makes this cosine square t. And so on. Okay, and now so we have sine, t prime of t. Again, we take the derivative of these things. Negative sine t times the derivative cosine t, first function times the derivative second function, kind of a concept, becomes negative sine t times negative sine t is sine square t, and so on. Okay, I simply differentiated this, folks. Now, in order to find t and t prime at the given point 1, 0, 0, I need to point this out. Please pay attention. We need to evaluate all these quantities at a point 1, 0, 0, right? What does that mean? That means the points x, y, and z coordinates are 1, 0, and 0. Okay, but our t, our r prime, all these things are functions of t. These are x, y, and z values, but we want the corresponding t. Is that doable? Yeah. So basically we are saying cosine t is equal to 1, and also sine t is 0. Further, natural log of cosine t is 0. Looking at all those values, can you tell what t must be? Cosine t is 1. So that means t could be 0, 2 pi, 4 pi, 8 pi, all kinds of things. But then t equals 0 is one of the solutions. And sine of t must be 0. We already said t must be equal to 0. Is sine of 0 0? Yep. Natural log of cosine t. Natural log of cosine 0. Cosine 0 is 1. Natural log of 1 is 0. Aha. So lowercase t being equal to 0 satisfies this condition. So basically, indirectly, we are being given the value of t when we are given the xyz coordinates of the point. Not directly though. And so let's find t of 0. And that just gives us 0, 1, 0 vector. And t prime of 0 plugged in here. Those values, and we get the vector t prime of 0. Have we succeeded in finding t? Yep, we found a vector t. I should have had a vector on top of this one. Okay, it's a vector t, not just regular t. Vector t is 0, 1, 0. And vector t prime of 0 is this vector. And why did we need this? Because n of 0, look, I put a vector on top of this n, but I didn't put a vector on top of this t nor on this t prime. Jeez. Okay, so t prime of 0 over the magnitude of t prime of 0, and just a simple calculation like that, folks. How do we find b? T prime of t of 0 crossed with n of 0 should give us the b of 0. T of 0 crossed with n of 0. And so just did the cross product. Ta-da, that's it. Cool. If you guys learn these simple concepts, I'm a happy man for this section. Okay, folks, that's it.